Okay, so here's a question for you. Have you ever really thought about why an amplifier for a TV signal is so wildly different from one for a radio signal? I mean, one is like this giant fire hose blasting you with information, right? And the other is more like a super focused laser beam. Well, today we're going to dive deep into why that is, and it all comes down to something called amplifier frequency response. So whether you're studying for a test or you're just a little bit curious about how all this tech around us actually works, let's get into it.
So, let's really break down that question. Why are they so different? Well, a TV signal, it's just jam-packed with all this visual info. You've got picture, you've got sound, it's a lot. A radio signal, though, it's way simpler. It's just carrying audio for one station. So yeah, it kind of makes sense they'd need different amps. But what's the real electronic principle going on under the hood? Well, the answer is this one single concept that is, no joke, critical to understanding pretty much all electronics.
All right, so that big, important concept, it's called frequency response. And honestly, the best way to think about it is like a report card for your amplifier. It's not just going to give you a single A or B. No, it tells you exactly how well that amplifier does its job across a whole range of different frequencies. Think of them like different school subjects. And that is the absolute key to figuring out what any amplifier was actually designed to do in the first place.
Okay, take a look at this graph. This right here, this is our secret weapon. It's called a frequency response curve, and it tells us everything we need to know. See along the bottom axis, that's frequency, going from low on the left to high on the right. And then, going up the side, that's the amplifier's output, or its gain, basically how much it's cranking up the signal. Now look at that nice flat plateau right in the middle. That is the amplifier's sweet spot. It's the zone where this thing is just crushing it, performing at its absolute peak.
And you know what? That sweet spot has a name. We call it bandwidth. It's the specific range of frequencies where the amp is doing its best work. But look what happens on either side of that range. The performance just drops off a cliff, right? So here's the takeaway, the most important part. An amplifier's bandwidth tells you exactly what it was built for. A super wide bandwidth, that's for our TV fire hose. A really narrow one, that's for our radio laser beam. See how it connects?
So a good question is, how do we know exactly where that sweet spot starts and stops? It can't just be a guess. Well, we use something called the half power points. These are the 2 points, one on the low end and one on the high end, where the output voltage drops to exactly 70.7% of its maximum. Now that number might seem random, but 70.7% voltage is the point where the power drops to exactly half. That's why they're called half power points. It's the industry standard, the official line in the sand that defines the usable range of an amplifier.
All right, so we're diving into the real-world limits here. I mean, in a perfect world, that bandwidth would be unlimited, right? It'd be just a flat line forever, and any amp could handle any signal you throw at it. But we don't live in a perfect world. In reality, every single circuit has physical limits. So, what's stopping us? What's the big problem that keeps us from getting that perfect performance? Let's dig in.
Well, in a perfect world, bandwidth is unlimited. But in the real world, we have to deal with two invisible forces that are kind of working against us. I want you to meet the two main villains of our story, capacitance and inductance. These guys are everywhere. They're in the wiring, in the components, even inside the transistors themselves. You literally can't get rid of them. And they both have a huge impact on how a circuit works with different frequencies, but in completely opposite ways. And here's where it gets super interesting. These two things, capacitance and inductance, they're polar opposites. So let's look at capacitive reactance first. Think of a capacitor like a bouncer at a nightclub that loves high energy. The higher the frequency, the easier it is for the signal to get past. It loves high frequencies. Now, inductive reactance, it's the exact opposite. It's a bouncer that prefers things calm and slow. It lets low-frequency signals pass easily, but it blocks the high-frequency ones. This whole idea that they do the complete opposite thing is the key to everything we're going to talk about next.
So let's just recap what's limiting our frequency response. It's these two forces, capacitance and inductance, and they are everywhere. You've got them in the wiring, in the components. You've even got this pesky interelectrode capacitance that's literally built inside the transistor itself, between parts like the base and the collector. You can't escape it. And all these tiny individual effects add up, and that's exactly why that nice flat performance curve we saw eventually has to drop off on the high and low ends.
Okay, enough about the problems. Let's talk about the solutions. And first up, we're going to tackle video amplifiers, our broadband solution. Remember, a TV signal is that fire hose of information. It needs a massive, super wide bandwidth to get every single detail of the picture across. So how on earth do we build an amplifier that can handle that kind of load?
So here's the specific problem for video.
Those high frequencies in the signal get lost because of all that stray capacitance in the circuit. Remember our bouncer that loves high energy? It's basically letting those high-frequency parts of our signal sneak out the back door and get lost. So what's the solution? Well, we have to fight back. And we do that with a trick called high-frequency compensation.
And the hero of this part of the story is something called a peaking coil. So remember how we said inductors are the total opposite of capacitors? Well, we can use that to our advantage. It's like fighting fire with fire. By adding these little inductors, these coils, into the circuit in just the right spots, we can counteract the bad effects of the capacitance. We can actually use them to boost the high-frequency response, right where it would normally start to fail.
So let's look at the first way to do this. It's called series peaking. See that coil labeled L1 in the circuit? Series just means it's placed right in line with the output path. So as the frequency gets higher and that signal starts trying to leak away through the capacitance, our inductor, the bouncer that blocks high frequencies, starts to push back. It basically blocks the escape route and forces the signal to stay on track, giving us that peak or boost right where we need it.
But okay, if you want the most effective method, you use something called combination peaking. And this is where the real magic happens. We use two coils. We've got L2 in series, just like before, and now we add L1 in shunt, which is just another path. By having them both work together, we get a way more powerful effect. This is the whole shebang. It's the method that can give an amplifier a super wide, flat response all the way up to 6 megahertz, which is exactly what you need for a good clean video signal.
All right, let's totally switch gears now. We've talked about video amps, the broadband solution, but what if you need the exact opposite of a fire hose? What if you need that laser beam? Well, that's the job of an RF or radio frequency amplifier. The perfect example is your car radio. You don't want to hear every station at once, right? You want to tune into one specific station and block out everything else. For that, you need a totally different approach, the narrowband solution.
The heart and soul of an RF amplifier is something called a tuned circuit. And get this, it's a clever team-up of our two main characters, a capacitor and an inductor, usually hooked up in parallel. At one very specific frequency, they work together to create a massive impedance, like a giant roadblock. But for every other frequency, they create an easy path to ground. It's like an open door. So only the one frequency you want gets amplified, and all the others get tossed aside. That's how you get that incredible selectivity. And we can even adjust how sharp that laser beam is. Take a look at the image on the left. This shows loose coupling. See how sharp and narrow that peak is? That's super selective, but maybe it's too selective. It could be so narrow that you actually chop off parts of the signal you want to hear. Now look at the image on the right. This is optimum coupling. The peak is a little wider, a little flatter on top. This is usually the sweet spot for most applications because it gives you a great balance between being selective and still getting the whole signal through cleanly. Okay, and there's one last little trick we have to talk about for RF amps. It's called neutralization. Now, remember that annoying capacitance that's hiding inside the transistor itself? Well, at really high radio frequencies, that little bit of capacitance can act like a feedback loop. It can cause the amplifier to go totally nuts and start oscillating, basically making its own noise. So neutralization is a clever way to fix that. It's like putting a pair of noise-canceling headphones on the amplifier. It feeds back a tiny bit of the signal, but out of phase, to perfectly cancel out that unwanted oscillation. It's what keeps the amplifier stable and clean.
Whew, okay, we have covered a ton of ground here. We started with the basic problem that limits all amplifiers, and then we looked at two completely different solutions, the broadband fire hose approach for video and the narrowband laser beam for RF. So now let's make sure all this stuff actually sticks. We'll do a quick recap, and then I've got a few practice questions for you.
All right, you ready? Let's do a rapid-fire recap of the key terms. Bandwidth, that's the amplifier's effective sweet spot. Half power point, that's the official edge of the bandwidth, the 70.7% voltage mark. Peaking coil, that's our little inductor hero that boosts high frequencies in video amps. Tuned circuit, that's the LC network that creates the laser beam focus for RF amps. And finally, neutralization. Those are the noise-canceling headphones that stop RF amps from oscillating. Got it? Good.
Okay, first practice question for you. What is the bandwidth of an amplifier? It's the range of frequencies that the amplifier is most effective in, measured between those two half power points.
Question number 2. What are the factors that limit the frequency response of a transistor amplifier? The two big ones, our main villains, are capacitance and inductance. And you find them everywhere, in the wiring, the components, and even inside the transistor itself. And last practice question, number 3. What components can be used to increase the high-frequency response of an amplifier? For this, we bring in the hero for video amps, the peaking coil. It's just an inductor placed strategically in the circuit to counteract capacitance.
All right, and to wrap things up, here's a final thought to take with you. Now you know the why behind these completely different amplifier designs, the fire hose versus the laser beam. So put yourself in a technician's shoes. If you had a circuit in front of you that was losing all of its high-frequency detail, where would you even start to diagnose that problem? What would be your first step? Because that is the moment all this theory becomes real-world practice. Thanks for sticking with me through this explainer.